We'll start in 1 minute. Today we'll continue with trigonometric substitution. The last time we just started this example. For this one we have a definite integral. The integrand is dx over the square root of 25 plus x squared. And the lower limit of integration is x equals 0. The upper limit is x equals 5. So since we have 25 plus x squared, we pick x to be 5 times tangent of theta. So that dx is 5 times secant of theta squared, d theta. And 25 plus x squared upon substitution becomes 25 plus 25 times the tangent of theta squared. And that simplifies to, using the identity, this becomes 25 times secant of theta squared. Okay, so in the numerator we've replaced dx with 5 times secant of theta squared d theta. In the denominator, we take the square root of 25 secant of theta squared to get 5 times secant of theta. And then the limits of integration, since we have this trigonometric substitution as a function of theta, the lower and upper limits must be values of theta. So we find the lower and upper limits based upon the lower and upper limits for the x values. Since x equals 5 times tangent of theta, when x is 0, we set 0 equal to 5 times tangent of theta. And that occurs when theta is 0. So the lower limit is theta equals 0. And the upper limit for x is x equals 5. Replace x with 5. 5 equals 5 times tangent of theta, or 1 equals tangent of theta. And that occurs when theta equals pi over 4. Okay, so we simplify the integrand. Uh, 5 divided by 5 is 1. Secant of theta squared divided by secant of theta is secant of theta. And then d theta. And what's the antiderivative for secant of theta? It's one of those basic ones that you should know. An antiderivative for secant of theta. Exactly, the natural log of the absolute value of secant of theta plus tangent of theta. And we're evaluating this between theta equals 0 and theta equals pi over 4. So we get the natural log of the quantity secant of pi over 4 plus tangent of pi over 4, and then minus the natural log of the quantity secant of 0 plus tangent of 0. Secant of pi over 4, well, remember, secant is the reciprocal of cosine. We know that cosine of pi over 4 is 1 over the square root of 2. So the secant of pi over 4 is the reciprocal of 1 over the square root of 2, or the square root of 2. Tangent of pi over 4 is 1. So we get the natural log of the square root of 2 plus 1. And then minus the natural log. Secant of 0 is 1. Tangent of 0 is 0. The natural log of 1 is 0. So our final answer is the natural log of the square root of 2 plus 1. So we don't need the absolute value symbols now because those are positive numbers. Hey, this is a run-of-the-mill type of problem, as I guess everything that we're doing is run-of-the-mill. Hey, this next example, the indefinite integral of dx over the square root of x squared plus 2x plus 5. Well, we have to make an alteration to help us out here. So we're going to focus on what's inside the square root in the denominator. Let's take a look at x squared plus 2x plus 5. And we're going to complete the square on x squared plus 2x. So remember what that means. Another way to describe completing the square is creating a perfect square trinomial. So if we focus on x squared plus 2x, when the coefficient of x squared is 1, to get a perfect square trinomial from x squared plus 2x, we take half of the coefficient of x and square it. So half of 2 is 1, 1 squared is 1. So we're going to borrow a 1 from the 5 and write this as x squared plus 2x plus 1 plus 4. The x squared plus 2x plus 1 is a perfect square trinomial, which means that it's equal to a binomial squared. In this case, it's x plus 1 squared. So our expression is transformed to x plus 1 quantity squared plus 4. And now we can use a Trig substitution. So the quantity that we're squaring is x plus 1, but that doesn't present a problem. We just assign x plus 1 to be 2 times tangent of theta. And when we take the derivative with respect to x, in terms of differentials, the left-hand side just becomes dx because the derivative of 1 is 0. And the right-hand side is 2 times secant of theta squared d theta. Okay, so the x plus 1 quantity squared plus 4, well, we're replacing x plus 1 with 2 times tangent of theta, and when we square that, we'll get 4 times tangent of theta squared. plus 4, and 4 times tangent of theta squared plus 4. Using a Pythagorean identity, this becomes 4 times secant of theta squared. Okay, so this is what's going to go inside the square root. So in the numerator, we write dx, which is 2 times secant of theta squared d theta. In the denominator, the square root of 4 times secant of theta squared. And a little bit more arithmetic. So 2 times secant of theta squared d theta in the numerator. And in the denominator, the square root of 4 times secant of theta squared is 2 times secant of theta. 2 divided by 2 is 1. Secant of theta squared divided by secant of theta is secant of theta d theta. We saw this integral a few minutes ago. So the indefinite integral of secant of theta d theta is the natural log of the absolute value of secant of theta plus tangent of theta plus a constant. For the indefinite integral, we have to do a little bit more work. We want our antiderivative, or the indefinite integral, to be expressed in terms of x. So that's where our trig substitution comes in. If x plus 1 equals 2 times tangent of theta, that means tangent of theta is x plus 1 over 2. So we'll use right triangle trigonometry to help us out. So if this is our angle theta, and if the tangent of theta is x plus 1 over 2, then we label the side opposite of x, or of theta, as x plus 1, and the adjacent side as 2. And then using the Pythagorean theorem, the hypotenuse is the square root of x squared plus 2x plus 5. Okay, so we're a couple of steps away. Secant of theta, using this right triangle, is hypotenuse over adjacent side. So it's the square root of x squared plus 2x plus 5 over 2. And then tangent of theta, opposite over adjacent, is x plus 1 over 2. And then plus a constant. Okay, this is an okay answer, but I'll take it a little bit further just to illustrate. When you see the book, or the answers in the book, you might wonder what they're doing or why they give the answers that they give sometimes. So this is, since the denominator of both rational expressions is 2, we can write a single rational expression in the numerator, the square root of x squared plus 2x plus 5 plus x plus 1 all over 2. And then using a property of logarithms, we can write this as the natural log of the absolute value of the square root of x squared plus 2x plus 5 plus x plus 1 minus the natural log of 2 plus a constant. The natural log of 2 is just a number, so it can be part of the constant of integration, and then write the final result as the natural log of the absolute value of the square root of x squared plus 2x plus 5 plus x plus 1, and then plus, say, c sub 1, where c sub 1 is the constant equal to minus the natural log of 2 plus c. But as I was saying earlier, or as I mentioned, this answer is okay. If you left that on as your answer on a test, that's perfectly fine like that. Okay, the next one, find the area of a circle whose radius is capital R. Well, we already know what the area of that circle is, but we're going to use a trig substitution and, in effect, derive the formula for the area of a circle whose radius is R. So, any ideas on how to start? Well, I'll attempt to draw a circle centered at 0, 0 with radius capital R. So the center is at the origin. So pretend like this is a circle. Okay, if this is in the xy plane, what's the equation for that circle? So if you remember back from intermediate algebra, you learned equations of circles in that class, if you took that class. Okay, the standard equation for this circle is x squared plus y squared equals capital R squared. If we solve this equation for y, first we'll subtract x squared from both sides. So y squared equals capital R squared minus x squared. And y has two solutions. Y is equal to positive or negative square root of R squared minus x squared. The positive square root represents the upper half circle centered at 0, 0 with radius R. And the negative solution is represents the lower half circle. So one thing we could do, we could use the upper half circle and integrate the positive square root of R squared minus x squared between x equals negative R to R, and that will give us the area of the upper half circle. But the area of the upper half circle is the same as the lower half, so we would just afterwards multiply that by 2. Right, remember from Calc 1, if you have a graph of a function in the xy plane that's above the x-axis, and if you integrate on an interval, then the value of that integral, of that definite integral, is just the area that's below the graph and above the x-axis. So that's all we're doing. So the area of the full circle will be equal to 2 times the definite integral from negative R to R of the positive square root of R squared minus x squared dx. Well, I'm debating with myself. There's another thing we could do to make it, might make it a little bit easier. We could just find the area of the upper right quarter circle if we integrate from 0 to r and then just multiply that by 4. So I'll go ahead and write that down. If we multiply 4 times the definite integral from 0 to capital R of the square root of capital R squared minus x squared dx. So either one of those is okay. But regardless, we're going to use a trig substitution. So our trig substitution is going to be x equals what? Yeah, x will be capital R times sine of theta. Capital R times sine of theta. And so dx is r times cosine of theta d theta. And r squared minus x squared, that's what's going inside the square root. That's r squared minus r squared times sine of theta squared. And this is all going to simplify to r squared times cosine of theta squared when we use the Pythagorean identity, right? Okay, so 4 times the definite integral. Well, our limits of integration have to be theta values. And the theta values are determined by the x values of the original definite integral and our assignment that x equals capital R times sine of theta. Okay, so when x is 0, the lower limit up here is x equals 0. In this equation, replace x with 0 and determine what theta is. If 0 equals r times sine of theta, then what's theta? 0, because sine of 0 is 0. So theta is 0. The upper limit over here is x equals r. So in this equation, replace capital X with, I'm all messed up. Replace x with capital R. So if r equals r times sine of theta, divide both sides by r, we get 1 equals sine of theta. And what's the value of theta when sine of theta equals 1? Pi over 2. So the upper limit is theta equals pi over 2. Okay, so we have the square root of the quantity r squared times cosine of theta squared. And then dx is times r times cosine of theta, d theta. So 4 times the definite integral from 0 to pi over 2. The square root of r squared times cosine of theta squared is r times cosine of theta. We multiply that by r times cosine of theta, d theta. The constant is r squared, so I'll bring that constant out front, so it's 4 times capital R squared times the definite integral from 0 to pi over 2. And then cosine of theta times cosine of theta d theta is cosine of theta squared d theta. And hopefully now a familiar identity for cosine of theta squared that is pretty handy when computing integrals, is 1/2 plus 1/2 times cosine of 2 theta. So 4 times r squared times the integral from 0 to pi over 2. And we replace cosine of theta squared with 1/2 plus cosine of 2 theta divided by 2 d theta. Maybe for convenience, it's not necessary, but since each of the terms inside the integral has a factor of 1/2, if we bring that out and multiply 4r squared by 1/2, we'll get 2r squared, and then the integral from 0 to pi over 2, and the quantity will be 1 plus cosine of 2 theta d theta. Okay, so now we can go ahead and find the antiderivative of 1 plus cosine of 2 theta. So we get theta plus 1/2 times sine of 2 theta. And we're going to evaluate this from 0 to pi over 2. So we're almost done. 2 times r squared. So first replace theta with pi over 2. So pi over 2 plus 1/2 times sine of 2 times pi over 2 is sine of pi. And then minus the quantity 0 plus 1/2 times sine of 0. So sine of 0 is 0. Sine of pi is 0. So the only thing that survives is pi over 2. So 2r squared times pi over 2, the 2's cancel, and we get pi times capital R squared, which we knew all along was the area. Okay, the next page. So this one show that the indefinite integral of dx over the square root of x squared plus a squared equals the natural log of the quantity x. I suppose that should be in absolute values, but so the natural log of the absolute value of x plus the square root of x squared plus a squared plus a constant. In the first case, use x equals a times tangent of theta. So we've actually already have experience with this one in particular for actual numbers for a instead of a squared. But let's go through the process. If x is a times tangent of theta, dx is a times secant of theta squared d theta. And x squared plus a squared is a squared times tangent of theta squared plus a squared. And that simplifies to a squared times secant of theta squared. Okay, so in the numerator, we'll replace dx with a times secant of theta squared d theta. In the denominator, we have the square root of the quantity a squared times secant of theta squared, so that will simplify it at a times secant of theta. So this is the third time that we've seen this today. A divided by a cancels, one factor of secant of theta cancels, so we get the indefinite integral of secant of theta d theta. So the indefinite integral of secant of theta d theta is the natural log of the absolute value of secant of theta plus tangent of theta plus a constant. Okay, but we have to replace theta with, we have to express it in terms of x. So our assignment, x equals a times tangent of theta. So that means tangent of theta is x over a. So we'll use right triangle trigonometry to help us out again. If tangent of theta is x over a, then in this right triangle, the opposite side of theta is x and the adjacent side is a. And the hypotenuse is the square root of x squared plus a squared. Okay, so the natural log of, instead of secant of theta, we write the square root of x squared plus a squared over a plus tangent of theta is plus x over a plus c. And my comments earlier, we took it a step further and combined the minus natural log of a with the constant. So that's what happened up here. That's why we don't, up here we don't have, we're not dividing by a inside the natural log. Does that make sense? Okay, that one was pretty straightforward. Let's do the same using this trig substitution. Well, sorry, it's hyperbolic trig. Use x equals a times hyperbolic sine of t. So it's for the same one. Hey, if x equals a times hyperbolic sine of t, then dx is a times hyperbolic cosine of t. And our x squared plus a squared, well, when we square x, we get a squared times hyperbolic sine of t squared, and then plus a squared. This is a squared times the quantity hyperbolic sine of t squared plus 1. So what's hyperbolic sine of t squared plus 1? Anyone know? Okay. Well, on another piece of paper. Just as a reminder, hyperbolic sine of t is equal to e to the t minus e to the negative t divided by 2. And hyperbolic cosine of t is e to the t plus e to the negative t, all divided by 2. So on the other page, we were looking at hyperbolic sine of t squared plus 1. So let's go ahead and square hyperbolic sine of t, and then afterwards add 1. So we don't have to write everything down. So in the numerator, we're going to square this quantity, e to the t minus e to the negative t. So e to the t times e to the t is e to the 2t. And then I'm going to subtract e to the t times e to the negative t, which is e to the 0, which is 1. So I'm going to subtract 1. And then I'm going to subtract e to the negative t times e to the t, which is minus 1 again. And then negative e to the negative t times negative e to the negative t is positive e to the negative 2t. And then we also square the denominator. 2 times 2 squared is 4. And then we're going to add 1. Okay, we'll do a little bit more arithmetic. In the numerator, e to the 2t minus 2 plus e to the negative 2t, all divided by 4. And we're adding 1 to it, but I'll write 1 as 4 over 4, so we have a common denominator. And then when we write this as a single expression with a denominator 4, we get e to the 2t plus 2 plus e to the negative 2t. And this is just equal to it's equal to e to the t plus e to the negative t over 2 squared, which is what hyperbolic cosine of t is. So I could have just told you that hyperbolic sine of t squared plus 1 is equal to hyperbolic cosine of t squared, but it's good to know sometimes how things or why things are the way they are. Okay, so now we know. Hyperbolic sine of t squared plus 1 is just hyperbolic cosine of t squared. Okay, so now we'll make substitutions. We replace dx in the numerator. Oh, I forgot. So dx is a times hyperbolic cosine of t dt. So in the numerator, a times hyperbolic cosine of t dt. In the denominator, we have the square root of x squared plus a squared, which becomes the square root of a squared times hyperbolic cosine of t squared. So the square root of that is just a times hyperbolic cosine of t. And a divided by a is 1. Hyperbolic cosine of t divided by hyperbolic cosine of t is 1. So we get the indefinite integral of dt. So what's the indefinite integral of dt? T plus a constant. Well, t doesn't look like the natural log of the absolute value of x plus the square root of x squared plus a squared. So now what? Well, remember what our assignment is. So x equals a times hyperbolic sine of t. And so that means x over a equals hyperbolic sine of t. Remember what hyperbolic sine of t is. That's e to the t minus e to the negative t over 2. So we want to solve this equation for t. So we're going to ignore the middle part. We're just going to focus on x over a equals e to the t minus e to the negative t over 2 and solve that equation for t. First thing I'll do is multiply both sides by 2. So we get 2x over a equals e to the t minus e to the negative t. And next, I'm going to divide every term on both sides of the equation by e to the t. And that's perfectly legal because e to the t is always positive. So if you multiply both sides of an equation by a positive number, you've done nothing wrong. So multiply both sides by e to the t, we'll get 2x over a times e to the t on the left-hand side. On the right-hand side, e to the t times e to the t is e to the 2t. And then minus e to the negative t times e to the t is minus 1. Okay, now I'm going to subtract 2x over a times e to the t from both sides so that the left-hand side is 0. But I'll put all of those terms on the left-hand side in the following order. So I get e to the 2t minus 2x over a times e to the t minus 1 equals 0. What we have is an equation that is quadratic in form. So the term on the left is e to the t squared. The middle term is minus a constant times e to the t, and then minus a constant. So it's quadratic in form. So we can use the quadratic formula to solve for e to the t. So I don't have capital X squared, but I do have e to the t squared. So I'm going to use the quadratic formula where the value of a is 1. That's the coefficient of e to the 2t. B is the coefficient of e to the t, which is negative 2x over a. And the constant c is negative 1. So applying the quadratic formula to this, I get e to the t equals negative b. So the negative of negative 2x over a is 2x over a. And then plus and minus the square root of b squared minus 4ac. So b squared, I'm going to square negative 2x over a to get 4x squared over a squared. And then minus 4 times 1 times negative 1, that's the same as subtracting negative 4, so I'm going to add 4. And then divide everything by 2a, or 2 times 1. Okay, now we'll just do a little bit of algebra and arithmetic. So 2x over a. Remember, e to the t is never negative. The solution that we would get by subtracting would make it negative. So we can ignore the solution that we get by subtracting and just add. So we get the square root of 4x squared plus 4a squared all over a squared, and then divided by 2. And so in the square root, since we're dividing by 2, that's the same as multiplying this numerator by 1/2. So I'm going to do that here. I'm just going to multiply 1/2 times the numerator. So we'll write 2x over a. And notice in the square root, in the numerator, we have a common factor of 4. So we can take the square root of 4 and bring that outside. And then the square root of a squared in the denominator is just a. And then we have the square root of x squared plus a squared. And now when we distribute multiplication by 1/2, we get x over a plus the square root of x squared plus a squared over a. And that is what e to the t is. So to solve for t, if e to the t is equal to this quantity, then how do we solve for t? Take the natural log of both sides. Okay, so the natural log of e to the t is just t. And then the right-hand side, the natural log of that quantity, x over a, plus the square root of x squared plus a squared over a. And then plus c, I guess. So anyway, that's what we wanted to get. Okay, there's about 5 minutes left. There's at least one problem from the last Wednesday's lecture notes that I want to get to. I can find it. Okay, this one, this is from our review day over chapter 7, sections 1 and 2. So the indefinite integral of secant of x to the third. So in this one, we rewrite secant of x to the third as secant of x times secant of x to the second dx. And then we integrate by parts. For short, I'll just write by parts. Okay, so on this one, assign u to be secant of x and dv to be secant of x squared dx. And if u is equal to secant of x, then du is secant of x times tangent of x dx. And if dv is secant of x squared dx, then what's v? It's tangent of x. Okay, so we'll write down what we get by applying the integration by parts formula. So that's equal to u times v, or secant of x times tangent of x, and then minus v du, minus the integral of v du. So that's tangent of x times secant of x times tangent of x, but we'll write that as tangent of x squared times secant of x dx. Then we're going to replace tangent of x squared with secant of x squared minus 1. So the quantity secant of x squared minus 1 times secant of x dx. So let's do a couple of things at once. We're going to multiply secant of x times secant of x to the second to get secant of x to the third. So we're going to subtract the integral of secant of x to the third. And then we're going to subtract the negative of the integral of secant of x. So that means we're going to add the integral of secant of x dx. So the left-hand side is the integral of secant of x to the third, but over here you see that we're subtracting secant of x, the integral of secant of x to the third. So when we add that to both sides, we get 2 times the integral of secant of x to the third equals secant of x times tangent of x. Let's go ahead and write down the antiderivative for secant of x. The indefinite integral of secant of x is plus the natural log of secant of x plus tangent of x. And then lastly, divide everything by 2. So on the right-hand side, this is what we get for the indefinite integral of secant of x to the third, and then dx. Okay, we're a little bit over times. If you're watching online, go ahead and sign in for attendance. Josh Anderson, William Andrews, Haley Coffin, Jason Cole, Nicholas Devlin, Sarah Gonzalez, Reckon Project. Good Mills. Okay, I think I have everyone.